Hi, my name is Joe Alexandersen, and I'm an assistant professor at the Department of Mechanical and Electrical Engineering at the University of Southern Denmark. Today I'll be talking about topography optimization in the context of parallel plate heat exchangers and showing you some simplified models for fluid flow in this context. So the motivation for this work comes from one of my colleagues and collaborators' projects called NEGEV, Next Generation Ventilation, which focuses on the design of climate modules for building ventilations. And this is done by passing air through stacks of PCM plates, so that is plates filled with phase change materials that is able to store thermal energy, and this is used to sort of decrease the energy consumptions of these ventilation systems. So inherently, this is a very difficult computational problem. So we have the phase change, the energy storage cycle is inherently time dependent. We have a large span of length scales, so we have a spacing between the plates in the order of millimeters, and the sort of whole system is on the order of meters. So we have very high requirements for our mesh. And then we also have turbulence because these are quite high flow rates that we have through the system. In the recent years, simplified models have become quite popular within especially topology optimization for fluid flow, and that's because they reduce the computational time. And my idea was, can we use some of the ideas from topology optimization for fluid flow in this context? So I'm going to try to approximate these stacks of plates with very thin spacing as sort of a porous media, or rather by incorporating the resistance term from passing through these thin spacings. So this was the origins of topology optimization for flow. That was the introduction of a resistance term based on the flow between parallel plates. So in 2003, Borvald and Pedersen did so for Stokes flow, and in 2005, Gersber Hansen et al. Extended this to Navier-Stokes flow. But the ideas were basically the same. So for Navier-Stokes, we get this equation here if we assume a fully developed flow profile in the through thickness direction. And we get these two non-standard terms. We get a scaling of the convective term, which is not so important. And we get this resistance term, which is due to the out of plane viscous resistance of passing through this spacing. This resistance depends on the thickness of the fluid layer here. And in Gaspar Hansen, they discuss that this is merely a algorithmic device to implement a continuous transition between viscous flow and zero flow. So the point here is that we have spaces of full flow or uninhibited flow with a certain thickness, and then we have regions of solid, which we approximate by having a very small thickness. So if we're doing topology optimization and we have distinct regions of fluid and solid, then everything is okay using this model. So if we go back to the stack problem here, we have two stacks of these PCM plates. We have 24 plates in each of these stacks, and we have 25 spacings. The spacing is around 3 millimeters, so that gives a fluid resistance coefficient of this number here. And the good thing is that we have these stacks, or these plates are in parallel, the spacings are in parallel, so the flow resistances are also in parallel. So that means we can look from the above here. We have this plane simplification of the climate module. We have the inlet here, the inlet chamber here, the distributor chamber. We have the two stacks. We have the outlet chamber and the outlet edge here. And then we can impose these fluid resistance coefficients in the stacks. We also have some for the distributor, inlet and outlet distributors. This is because we still have some out of plane thickness here, but it's big, so the resistance is small. And we get this flow field here for certain flow conditions. But what is weird is that we have very small velocities between the plates here, which seems weird because we have a very high reduction in the actual volume that the flow is passing through. But that's because just including the fluid resistance term does not account for mass conservation. So if we have a field where we have a varying thickness, we have to take mass conservation into account. And we do that by including the height variation, and we get two sort of augmentations to the classic divergence constraint that depend on the thickness and the thickness gradient. And if we include these in our model, so we both have the fluid resistance term dependent on the height or the thickness, but we also have now the incompressibility condition also depends on the height and the variation of the height. So this was our old results using only the fluid resistance, and this is new one where we account for mass conservation. So because we have a much lower total volume here inside the stacks, the velocities are much bigger than they were using just the resistances. And this is more accurate, closer to the full 3D simulations we have. So if we zoom in and look closer on these PCM plates, we can look at a single spacing between two of these plates. And we see that the plates have this quite complex surface topography. There are several reasons for this. Some are there because we have to be able to fill these plates using the PCM solution. These in the middle here are sort of to conjoin the two sides together. Some of these are corrugations that are there for, for stiffness purposes because we have quite a heavy solution. Um, and as we can then sort of imagine two of these plates and we look at the thickness of the fluid layer in between, we can sort of create a surface height field or a fluid height field uh, similar to these topographies of these plates. And we can simulate the flow between two of these plates. And here we see for our 2D model and a full-blown 3D model. And it's very hard to see the difference, so I better just show here that the top one is our 2D model and the bottom is a full-blown 3D model. There are some differences, and that's fine, but overall the resemblance is very good. So now we have an accurate model for this kind of varying topography fluid flow. So let's do some topography optimization. So for the climate module, it's a lot about flow distribution. So these examples are sort of inspired by that. We're looking at the distribution of fluid flow fields here. So we have a single inlet here on the left, and then we have three outlets on the right where we want to distribute the mass flow equally, so to 1/3 to each outlet. So our objective function is to minimize the discrepancy from having 1/3 mass flow at the outlets. We have a maximum and minimum thickness here and a Reynolds number of around 150. So here we see the topography field, so the height of the fluid layer. Here we see a 3D representation where we can see the smoothly varying topography. Here we see the fluid flow field for the plane model and for the full 3D model. And these are basically the same. The distribution is 1/3 to each outlet in both models. But this has a relatively large pressure drop because we're using some thin regions where we're passing flow through to sort of distribute it. So if we change the problem slightly, we use these mass flows as constraints, and then we try to minimize the pressure drop from inlets to outlets. So we get something like this, resembling more something from topology optimization. So we actually see that it goes to the bounds. This is the minimum thickness. We see the maximum thickness here, generating some channels with maximum thickness. This is also seen in the 3D representation over here. We see the flow field, and again, these are basically the same for 2D and 3D, which is great. We can take it one step further. So instead of having three sort of discrete small outlets, we now have one big distributed outlet. And we're trying to sort of minimize the variation along this outlet edge. Do that by constraining the standard deviation of the velocity across this edge, and then minimizing the pressure drop. get this surface topography field here. In 3D, we can see it's kind of like an M topography here, which sort of distributes the flow uh, out into the two edges here, reduces what comes in, so it's more or less even at the outlet. Again, 3D model is very, very good. If we compare this to just having a constant thickness of 1 centimeter of the fluid layer, so having a relatively small thickness in itself, this resistance that it gives helps to distribute the flow more evenly. We see the blue line here. The green line is the optimized field. We have a significantly lower pressure drop at more or less the same standard deviation as the constant thickness plate. So this topography change really does make a difference. So we can make it a little bit harder by now having the inlet off center and then still having the same problem. We get this topography here. 3D, it looks really nice. And again, the 2D and 3D results are more or less identical. So now we have a flow model. We have a way of optimizing the topography for flow. But in the actual practical application, we want to sort of indirectly control the flow distribution through optimizing for the thermal field. So we also need a thermal model here. We can derive that akin to the sort of fluid model. These are inspired by these three papers up here. There are several more recent papers also on these sort of pseudo 3D approaches. We can make a temperature model that captures very well this 2D problem that we collapse to 1D. We can look at the single spacing model where we're looking at the spacing between two heated plates. We get also that the plate surface temperatures are quite well captured. The velocity is overall very good. This is for some slices across the spacings. In lines, we see the full 3D, and the points are the plane model. Here we see the surface temperature of the plates are also okay, well captured, but not quite as good. We have quite a high discrepancy near the inlet side, but I think we can resolve that in the future. So in order to conclude here, the resistance term from lubrication theory, that's sort of the origins of topology optimization for fluids. But it is restricted to topology optimization when we have infinitesimal minimum thicknesses. So that is when we have full fluid and we try to emulate a solid. By augmenting the incompressibility condition, we can fix mass conservation and allow for varying thickness distributions. This allows to optimize the topography of these relatively thin fluid layers with a very high accuracy. So we have a simplified model now with a good accuracy. We can reduce 3D to 2D models. We get like I said, good accuracy for low to medium Reynolds numbers. Capture the dominant features of these flow and temperature solutions. And this allows us to potentially go to the transient situation. Now we have a 2D model instead of 3D model. It's easier to include the time dependency when including the phase change materials inside the solid. Also, the flow instabilities are easier to capture when we have a lower dimensional model. And we can combine this topography description of the fluid flow spacing with a topography description of the plates in order to accommodate for mechanical and thermomechanical effects. And with that, I thank you for listening. And here is a list of references. And please do check out my website. And if you have any questions, attend the live session or write me an email at this address here. Thank you.